Today we're going to go on to another one of the big ideas of calculus, and that is a definite integral. So if we have a function f that's continuous on a closed interval from a to b, and then we take that closed interval and we partition it, divide it up, into n subintervals of equal length. So for a general Riemann sum, they don't have to be of equal length. For this, we're going to do it in equal lengths, partitions. And that partition is going to have a change in x of b minus a divided by n. Right? B minus a is the width of the whole area. And then we're dividing that up into n subdivisions. So each one is going to be b minus a over n. That's your delta x. Then, if we take the limit as n goes to infinity, so in other words, we're going to take an infinite number of little subdivisions of the summation as n goes from 1, as k goes from 1 to n of f of c sub k times delta x, where c sub k is some arbitrarily chosen value in the kth subinterval. So in each subinterval, we're going to pick a little x value. We're going to substitute that in. That is the definite integral of f over the closed interval from a to b, and it's written this way. You've seen this symbol yesterday, if never before, when one of the problems we were looking at. That is the integral sign. It's supposed to, and you'll see it in your book and stuff, it kind of looks like a stylized, very tall, very skinny S. That's to remind you that it is a Riemann sum. Okay, a lot of times math symbols are just like a plus sign. Why is that the sign for addition? Who knows? But a lot of symbols in math are to remind you of something. And it's written as the integral from a to b of f of x dx. So again, this is the integral sign. A is called the lower limit of integration. That's where you're starting. B is the upper limit of integration. That's where you're finishing. F of x is called the integrand. It's what you're taking the integral of. It's called the integrand. And dx tells us that x is the variable of integration. Right? What are you taking the integral of with respect to? Right? Just like we do with derivatives. And we're actually going to, I think on Tuesday of next week, if I remember correctly, no, it's got to be some other time. Anyway, we will be doing the fundamental theorems of calculus, which actually join the integrals with derivatives. When people first started working on these, no one knew that the two were related to one another. It turns out they're inextricably related to one another. All right, so if our function f of x is non-negative and integrable, sort of like, where you can take a derivative of something, we call it differentiable. Here, this is integrable over a closed interval from a to b, then the area under the curve of y equals f of x from a to b is the integral of f from a to b. So when we were doing these, remember we looked yesterday at our Riemann sum, and it was all areas of those rectangles. And the areas of those rectangles approximated the area underneath the curve. What we're doing here is we're saying, instead of doing like the example we did yesterday where we only did 3 subintervals and it was really, really boxy, think of that as being a little bit like having a super pixelated picture, right? Where the pixels are so big you can actually see the rectangles or the squares that they're made out of. Well, what we're doing here is we're going to do an infinite number of rectangles. So we're going to have this lovely smooth thing that perfectly follows f of x. Now, occasionally you will get asked things like this, where it says evaluate this, and you're like, I don't really know. Well, what you have to do at this point is, and actually for this particular one, even later on, because I don't know any good way to do this problem, is to go, okay, if I had y equals this function, what does it look like? Is it something where I can figure it out geometrically because of areas of various geometric figures? Most of the time, it's rectangles, triangles, trapezoids. You get a lot of things that are straight at the top. This is an example of, and it's the only one that I know of, where it's not straight at the top, but you can still do it. And here's the deal. If we have y equals the square root of 16 minus x squared plus 3, if you were to subtract 3 from both sides, you get y minus 3 is the square root of 16 minus x squared. Square both sides, and you've got y minus 3 quantity squared is equal to 16 minus x squared. Add x squared to both sides, and you have x squared plus y minus 3 squared is equal to 16. You should recognize that. What is it? It's a circle. And what do you know about that circle? A couple of things.
Radius is 4.
Right, the radius is 4. And the center?
0, 3.
Is it 0, 3? Okay, so we know all of those things. The other thing is that while this is a circle, this isn't quite. It's only the top half of the circle. And the reason it's only the top half of the circle is this square root is only the positive root. If you want the top and the bottom, you would have to put a plus or minus here to get the top of the circle and the bottom of the circle. All right, so hopefully you can look at this and go, okay, yeah, I don't have to go through all these steps to figure out that it's a circle with a radius of 4 and that it's centered at 0, 3. But, so let's see. This is centered at 0, 3 with a radius of 4. And again, it's only the top half of that circle. If my integrand is non-negative, then the integral will be equal to the area below this curve. Well, the area below that curve is made up of two different parts. So square root of 16 minus x squared plus 3 dx is going to be equal to, I've got this rectangle down here on the bottom which has a width of 8 and a height of 3. So that's going to be 24. Plus I've got half of a circle where the radius is 4. So this will be 24 plus 8 pi. we don't dwell on these all the time because once you've done it, it's like, okay, yeah, it's just an area thing. And I think you only have maybe one homework problem on it, and then it's going to show up again at some point, and you're likely to have forgotten it. Try not to. Okay? I actually saw one of these on an international version of the AP exam where they had to know that. And sometimes the nice people at College Board put things on the international version, which is one that they allow us to see, to tell us this is going to be on the operational, which is the one that most people in the United States take sometime in the next few years. They kind of tip their hand rather, not tip their hat. All right, now, well, what if f of x is not all non-negative? If f of x has both positive and negative values on the interval from a to b, then the integral from a to b of f of x dx is equal to the area above the x-axis minus the area below the x-axis. So, page 2. Let's use the fact that the integral from 0 to pi of sine of x dx is equal to 2. Later on, you'll learn how to do that without being just told what it is. But for now, don't worry about it. To find the integral from negative pi to pi over 2 of sine of x dx. Okay, so what they've told us here is that the integral from 0 to pi, which is just that first arch of the sine curve, that this area is 2. Then for this one, they want us to go from negative pi to pi over 2. So we're only doing this much. Because this first arch is below the x-axis, we're going to take the opposite of its area. So that'll be negative 2 plus, because of symmetry, I can say, well, I only went to pi over 2. That's going to exactly split this in half, and the whole area was 2, so this area is 1. So my answer is negative 1. The next one is one where they test out some of your algebra understanding. We've got sine of x minus 2. What does that do to the sine curve?
Shift it right to.
It shifts it to the right too. So instead of going from 0 to pi, it's going to go from 0 to 2 plus pi. Well, that's exactly what they asked us to find, is the integral from 2 to pi plus 2. So that's just 2. All right? We're not going to start learning rules for these, but one that we will, and I think it's a pretty easy idea, the integral of a constant. If you have a function f of x that's equal to c, some constant, then the integral from a to b of f of x dx is the integral from a to b of c, I'm just replacing the function with what it is, whatever that constant is, dx, is going to be c times b minus a. B minus a is going to be the width, c is going to be the constant height, it's just a rectangle. So, for example, this one, the train travels along a track at a steady 65 miles per hour from 1 a.m. to 3 a.m. Express its total distance as an integral and then evaluate the integral. So the total distance is going to be the integral from 1 to 3 of 65 dt. Because 1 and 3 are times, I used t. So since that's the velocity, if we take the velocity times the time interval, we get distance, right? And that's really what you're doing graphically. If this is up here at 65, and that's 1 and this is 3, the integral finds this area. And this is miles per hour, and this is hours. So we're multiplying the miles per hour times the change in hours. So that's just going to be 65 times 2 is 130 miles. And it seems a little crazy to do a calculus problem for that. But what if this isn't constant? We'll get to that where we're putting in some function and figuring out, well, how far did it go during that time? So if you have that rate of change over an interval, the integral tells you how much change you had. All right, in addition to continuous functions, functions that are bounded on an interval with a finite number of discontinuities are also integrable. This one I've seen, not this question, but I've seen diagrams that use this idea on the AP exam. So here, I've got the integral from -1 to 2 of the absolute value of x over x. Now, the absolute value of x over x doesn't exist at 0, right? But for anything greater than 0, the absolute value of x and x are equal, right? So that's just going to be 1. And for any value of x smaller than 0, less than 0, that's going to be -1 because we're going to have a positive over a negative. So if we're going from x is -1 to 2, since there is no infinite behavior, right? If there's infinite behavior, we're going to have to do something else, and we'll learn about that a ways down the road. But it's definitely finite, and there's a finite number of discontinuities. There's just one discontinuity, right? There are functions with infinite discontinuities. You're like, how does that work? It gets complicated. But since it's finite here, all I got to do is go, okay, this is area below the curve, and it's 1, so that's -1. This area is above the curve, and it's 2, so this is equal to 1. All right? Okay. Now you get to learn something else that's cool. So remember, there are 4 things you need to be able to do with your calculator. The first 2 are not calculus things. They are graph in an appropriate viewing window. The second one is be able to solve an equation, right, where you have blah, blah, blah equals blah, blah, blah. Either graph both of them and see where they intersect, or subtract one of them over and find the 0. I always find the zeros. The third one was find the numeric derivative, the estimate for the numeric derivative, right? You remember doing that. Students tend to forget that one because it just doesn't get done as often, but you can, right? The fourth one is be able to evaluate a definite integral. You can do these on your calculator if you have the formula for f of x. So you can do this two different places. You can do it on the graph screen, or you can do it from the home screen, and I'll show you both. So if you're doing it from the home screen, if you go into the math menu, and remember the numeric derivative was 8 on that list. Number 9 is the definite integral. And fortunately, in the last update, you didn't have to speak computerese to be able to put this in. You put it in exactly the way that it looks. The lower limit is 0. The upper limit is 1. Our function is x squared times the sine of x. The one thing that does look different is your calculator automatically opens a set of parentheses for the argument on sine, and we usually don't if it's just a single term. And then you have to tell it that the variable of integration is x. So it's 0.223. You can also do this from the graph screen, which is kind of nice. Sometimes if you are, especially doing a free response question, where you're going to do multiple things with a particular function, a lot of times on that, the best thing to do is immediately graph it, so that then if you need to take the derivative, you don't have to type it all again, and then you do the integral, you don't have to type it all again. You can just use y1 or y2 or whatever it is that you're doing. So if we graph this, let me get rid of this stuff. So this is 4 over 1 plus x squared. I'm going to do a zoom standard so I can kind of see what this thing looks like. It's like a little mountain. I want to evaluate the integral from 0 to 1. There's two ways I can do it. I can do it straight on the graph screen. If you do second trace, which gets you into your calculate menu, notice number 7. Probably never noticed that. By the way, you can also do the numeric derivative from your graph screen. We'll go down to number 7. And it asks for the lower limit, that's 0. The upper limit, that's 1. And one of the nice things is it goes ahead and colors that in for you to remind you, oh yeah, that's the area underneath that curve. And it's 3.14159. Huh. That area is pi. And you're like, where did they get pi from out of this? Well, what derivative do we take where we get 1 over 1 plus x squared?
Tangent.
Not tangent, but you're leaving off part.
Inverse.
Yeah, tangent inverse. That's why this works out that way. It has to do with the tangent inverse being involved in it. Oh, and where is tangent equal to 1?
Pi over 4.
Pi over 4. And notice this is being multiplied by 4. Yeah, this is pretty interesting. Now, if you are doing a whole bunch of other things, you can do this from your home screen as well. If you do math, and you'll probably get to the place where you just type the 9 rather than scroll down. Math 9, this is the integral from 0 to 1 of, and rather than retyping it, if you do alpha trace, you get y1. You're like, oh, okay. This is especially nice if you have multiple things you need to do. Let's say that for some reason you need to have y1 minus y2. Instead of having to type all of that, you can just put y1 minus y2, or y1 squared times pi or something. There's all kinds of things you can do, so you don't have to keep typing that again and again and again. Okay? Okay. Well, that is it for today.